Okay, so let's move on to this next section. We're talking about building models from data, and the models we're going to be building are exponential models, maybe logarithmic models, maybe even logistics models. Okay, so let's look at that first problem again that they gave us. They're talking about the strain of bacteria placed into a petri dish at 30 degrees Celsius. And it's allowed to grow, which means I'm dealing with a growth model, right? And then they give me all this stuff about what they're doing by measuring it with an optical device and everything else, and that all sounds good. But for us number crunchers, I don't really care how they conducted their experiment. What I need is their data. So once I got their data, they wanted me to fit it to an exponential function. So here's the deal. You need to input that stuff into the calculator. So we did that in a previous lecture. Remember, you have to go to that stat button and clear out all your lists and then input it again. And you do your inputting. I've already done my inputting. And then when I went to stat again and calculate what I punched in, because I'm looking for an exponential model, on my TI-83, I chose number 0, which said EXP REG, which means exponential regression. And they want us to round to 2 decimal places. So my calculator has given me these numbers for my A and my B. Which means my equation, my exponential model that we're looking for is y equals 0.2601 times 1.333 raised to the power of x. Good? Okay. Now, they want me to draw a scatter diagram. I'm going to let you draw that scatter diagram. Again, we've done that before in a previous lecture. You need to get to that stat plot and turn it on, okay? So I'm going to leave part B to you. And yes, this was part A. Part C wants us to rewrite this particular exponential function in the function I'm used to seeing, in the growth model function I'm used to seeing. And what they gave me was this. Isn't this our normal growth model? Except, you know, they used N instead of P, but it's the same thing, is it not? Okay, which means these two functions need to be equal to each other, don't they? Because they need to be the same. And in math, the same means equals. So, that's exactly what I'm going to do. I'm going to make them equal to each other. Whoops. Might help if I don't put the equal to sign too early, right? Now, I'm going to tell you right now, a lot of this part B is visual. So see if you follow along with me. A lot of this is visual. What I'm noticing is this. I'm noting this is the exponential part, right? And since this is equal, it should be equal to the other exponential part. Are you with me? Which means this n sub 0, which means the initial amount, needs to be equal to this 0.2601. So I just found that initial amount. Good? Okay. Now, again, you know as well as I do, to write this growth model, I need not only the initial amount, but I need the K. I need the rate, don't I? Okay, so remember what we just said. We have these two exponential parts that are supposed to be the same. So I'm supposed to have e to the kt, because this is what it looks like if they're supposed to be equal. Exponential should be equal to exponential, right? And now I'm looking and I'm like, I've got 3 variables in here. That's true, we do. Except they told us that x was time. So instead of writing x, we could write t. Couldn't we? And this is lovely because now I only have two variables. And I'm going to do a little rewrite on this side. This is e to the kt, right? This is e to the k times t. Agreed? Well, look. If that's multiplication, doesn't that mean that it could have been written in this manner with the parentheses between the k and the t? Because that means multiplication, doesn't it? Okay, so on this side, couldn't I basically say this base, this 1.333 is, right? Which means e to the k has to be equal to this base. Which means k is equal to the natural log of this lovely decimal. Cool? Which means my exponential growth model could be rewritten as my initial amount, e to the kt, and my k is this natural log. Got it? Okay, so far so good, right? Part B was all visual. Don't read too much into Part B. It truly was visual, except for this last computation right here of actually figuring out what K was. All right, so pardon me, this was Part C. My goof. This was Part C. Part D wants you to actually graph. Part D wants you to take all the data and graph it with either this function or this function. And it doesn't matter which one you graph it with, you're going to basically get the same graph because these two functions were supposed to be equal to each other, weren't they? All right, now Part E wants us to predict the population at 7 hours. Now notice it said it didn't care which model we used. We could use this one, the one the calculator gave us, or we could use this one, the one we found. So it's totally your choice. And again, it doesn't matter. It's totally your choice because when you set it up, you could say y at 7 hours is equal to punch that into your calculator, or you could say n of 7 hours is equal to and again, it doesn't matter. Whichever one floats your boat. And if you want to do them both to see if it truly gives you the same answer, be my guest. Do them both, and you will get the same answer. So, did you plug them in? Yes? Good. I ended up with 1.95. Did you? Either way, I ended up with 1.95. Hopefully you did also. Now, this last part for this problem. They want us to, again, either use the function that we got from the calculator, which would be this first one, or the one that we derived, which would be that second one. And they want us to determine or to predict when that population is going to reach 0.75. Now, they didn't give me any units, so I can't give you any units and say grams or anything like that. All right? So, regardless of which one you use, you're going to get the same answer. So, this is part F. and they want to know when, so I could set up this problem. I could set it up using the one the calculator gave me. And solving means I'm going to divide both sides by that 0.2601. And to get this exponential out, I have to take the log. And that's going to be interesting. So I'm actually taking the log of the base, 1.333, of this lovely fraction. Which means in order to figure this out, you got to use the change of base formula. And you're like, what was that again? Well, change of base formula says, and I'm going to use base 10. And I'm going to get myself a little bit more room to show you what that looks like. Okay, so I'm going to write this up here. That means I'm going to take the log base 10 of the original, which was the 0.75 over 0.2601, and divide it by log base 10 of the old base. That's what that meant. So you punch it in. I've already punched it in. And I got 3.7 for my time. Did you? Okay. And I'm going to show you how to compute this using the other one. Because some of you are like, I wanted to use the other one instead. Well, that's great. Use the other one instead. So for this one, I got x is approximately 3.7. Okay. Maybe you decided to use the other one. Whoops, my decimal's in the wrong spot. Sorry. And to the t times this natural log. So there's your setup, right? First thing you're going to do, divide by the 0.2601. Gee, that looks familiar, doesn't it? Next thing you're going to have to do is get that base e gone. So yeah, you're going to have to take the natural log of both sides, aren't you? Next thing you're going to have to do, you're going to have to divide by that natural log of the 1.33, right? So here's the interesting thing. We ended up at the same place. And I know some of you are like, what do you mean we ended up at the same place? Remember when you use the change of base formula, I can either change it to base 10 or I could change it to base e. Believe it or not, right here, natural log of 0.75 divided by 0.206 divided by this other natural log is exactly the same as this one, except one's base 10 and one is base e. But the change of base formula allows me to change it into any base I want, and I get the same answer. So believe it or not, you ended up right at the exact same place. Cool? Okay, so I showed you on both of them. Your choice which one you wanted to use. But now you see them on both. So hang in there. I got Okay, so let's look at this last one. This last one gave us this huge data chart with these humongous numbers, and they're talking about the population of the United States from 1900 to 2000 in increments of 10. And they gave us this logistics model, and they're like, hey, create a logistics model. Find me a logistics model. So first things first, you're going to have to punch that data into the calculator using that stat button again. Remember? Just like we did in a previous lecture. And then you're going to have to go, at least in my calculator, and my calculator is a TI 83, I had to go to letter B, which said logistics. And then I had to tell it my two lists to use, which was L1, L2, right? L1, L2. And then I hit enter. And yes, believe me, you're going to wait a few minutes because that calculator is doing a whole lot of number crunching. Those numbers are extremely large and they're fitting it to this model. So once you do that, this is what we get, A, B, and C. These are my A, B's, and C's. Now mind you, in the X column I put the years. In the L1 column I literally put the years. I put 1900, 1910, etc. Some other examples you're going to work with will tell you instead of 1900, put time equals 0. But they didn't say that here. So I put 1900, 1910, etc. Got it? Okay. And then I wrote the logistics model right here with my A, B's, and C's all in place. Cool? Lovely, isn't it? And now they want me to actually create a scatter diagram. So you know how to create the scatter diagram, get to that stat plot, and go for it. And then part C wants you to literally graph this model with the scatter plot. Be careful when you plug this into your calculator under the y equals. Be careful. Use extra parentheses to make sure it's all looking okay when you graph it. Okay, but let's get to part D. Part D is that carrying capacity. And we've spoken about that carrying capacity before, have we not? The carrying capacity is as time, or in this case x, because x stands for time, as x goes to infinity, right? Remember what happens here? This part basically becomes 0, which means when they ask for the carrying capacity, I'm basically getting the number in the numerator. I have 924,502,531 people. That's the amount of people according to them, the United States could hold. Good? Okay, let's get to part E. Part E wants to know the population in 2012, doesn't it? So my x is equal to 2012, isn't it? So if you allow me, by x, which was time, and here I'm going to put 2012 in its place. And when I do that, you punch it in your calculator. I've already punched it in mine. I ended up with 313,118,234 people. That's a lot of people. And then the last question was, when is that population going to reach 350 million? Which means in this case, y equals 350 million. And then they want me to solve. You with me? And boy, that looks like a lot of fun, doesn't it? Okay, so let's do it. Why? Because I know some of you are going to want to see the algebra in terms of how the heck do I get this solved. Because this is not a fun looking equation. And I get it's not a fun looking equation, but nonetheless, it's your algebra skills that need to be sharpened in order to solve these not so fun looking equations. By the way, I know most of you are heading into calculus, considering this is a pre-calc lecture, so you need to make certain that you have your algebra skills honed very well. So let me set this up. We have 350 million equals this 924 million, etc. on the top, over this lovely denominator, times this. Okay, so what do you think the first thing you're going to have to do is? This looks like something we've already solved in a previous lecture. In exponential and growth models, we solved something that looked like this. So hopefully you remember. Yeah, I am going to make the left side into a fraction, and I am going to cross multiply, because that will make life a little bit easier. Which means I'm going to get the 350 million times that denominator. And you're right, I'm being lazy. I don't want to write the denominator out. Right? And then my denominator is going to be equal to this lovely fraction. And then I'm going to be honest with you. Here's what I did from here. I did put this fraction into the calculator so I could see what it looked like. And no, I did not erase it out of the calculator. Okay? I got this fraction, and I'm going to write it in parentheses here just so you can see it. I got this fraction to be about 2.64. Don't erase the number out of the calculator. Leave it in there. You don't want to do any rounding. So, my denominator is this lovely number. And it's approximately equal to this decimal. I minus the 1 on both sides. And then I had to divide by this scientific notation number. And I ended up with this lovely scientific notation number. And then you got to get the e away, right? Which means, that's right, take the natural log of both sides. So I end up with, so far anyway. Again, please don't erase this decimal out of your calculator. And then I have to take this let's see. So, just to make sure we're on the same page, because I know some of you actually took the natural log of this, I got approximately a negative 31.16. Don't erase the number. And then I do the division, and I get approximately 20.23. Whoops, not point. Sorry. The year 2023 is approximately when, according to this model, the population will reach 350 million. Cool? This model is truly a plug-and-chug model, this whole thing. So it's a matter of you being very careful when you do your work and being meticulous and writing every step down. These logistic models, you could get lost in them very easily. So every little step. Got it? Okay, so you have fun with this section, and I'll catch you